And one of my favorite things about Scylla is that it runs with OKPerf with the absolute worst design schema, the crappiest hardware configuration, and the stupidest operator, me, setting things up at the start. There is a world of optimization to be done to perform well at production scale, but normally it just works. So Avid's presentation will be around how to set up your hardware, how to configure it to get the best performance. You're going to hear tips and tricks how to really set up Scylla great. My session is going to be about your client application. What do you need to do on your application side in order to get the best performance, if that is what you're looking for. And when users approach us on the Slack channel or have questions, the number one question we have, did you install scylla-grafana-monitoring? So if you hadn't, please do. But a lot of the users don't do it till they have an issue. And my session is about why you should use scylla-grafana-monitoring when you develop your application and what it allows you or will allow you while you're developing your application. So Scylla exposes a lot of metrics, hundreds of metrics. A lot of them have to do with how Scylla ticks, internal parts of Scylla, how they interact with. Others have to do with how Scylla interacts with your hardware. Is it working well? Do we have any queues filing up? Are we getting any delays from the hardware? Another subset has to do with the cluster. How is the cluster doing? Again, we're running a distributed database, so a query will end up probably in more than one node. But a subset of those has to do with how good you've written your application and how good you've set it up to work with Scylla. So my session will be focused around these metrics and a bit about data modeling. So for the sake of this session, I've written a sample application. And the sample application is written in Go. It's following the Go SQL example, so I didn't create any new issues. I just copy code and extended it a bit. And it's normal. When you start off, you copy code from somewhere and start augmenting it for whatever you want. The question is, did you catch all the items that you should have fixed before you go on to production? And there is a cost when you catch it. If you catch those things earlier on, instead of building strings using prepared statements, it's much easier to fix at the beginning. So again, that's my application. But a side note, I'm not a Go developer. Or to quote Hendrik, that made it Go-ish, it looks like a C++ developer hacked some code in Go just to show something. So I apologize if it's not that slick to the Go developers, but it's already up. And the sample application is based on two different tables. There is a tweets table in which we insert the tweets, and there is a timeline table into which we insert the information the user is interested in. So if I'm following a user, my timeline will have the tweets coming for that user. We added an additional field called liked, in which I can mark tweets that I'm interested in or liked. And again, for each user tweet, we insert into the tweets table, and that is a statement. For each user following follower of a user, we insert into the tweets timeline of that follower. In the sample application, we have a single query in which we're reading from the timeline and reading only the top, the first 50 lines, or the last 50 events. The setup, so the sample app starts with 4 nodes, a single client, a single cluster. And let's get it running. So I have here a 4-node cluster running in Docker, not yet with Docker Compose, but it will be. And let's start the client. So I've created a new dashboard. This is not yet live. It's part of the sample app. We'll probably propagate it later to the default dashboards. But this dashboard shows how good your application is running. So starting from the left, let's start tackle items. And what we see here is only 1% of the requests are prepared statements. So I'm going to stop this. And to make it easy for me, can we switch over to your display, please? And the pointer is not working. So what I show here is that 1% of the requests are prepared statements, and then you have the numbers. So let's fix that. And to get the gauge into green, 100% of your requests need to be prepared statements. And why is that? So when you're sending a string to Scylla, which holds the request, Scylla needs to parse it. It needs to figure out which table you're accessing. It needs to find the columns that you're inserting into. It needs to validate that the query is correct. It needs to extract the values from the columns. So all of this repetitive work is something that is happening in each request. And that is saved when you're doing prepared statements. This parsing and building of a template is done only once for the prepared statement. And afterwards, you can reuse that. In addition to that, again, if you're after getting the best performance that you can, you're actually hurting yourself. This additional processing is costing you time. So we are doing processing and then doing the statement itself. And that adds latency. On top of it, it doesn't allow us to do optimal routing. So in step 2 of the application, we're changing. We're changing the prepared statement from being a simple build string into a prepared statement in which we're building the template and then passing the arguments. In GoSQL, that's the simplest form I found. OK, so instead of switching back and forth, and for the essence of this talk, only the first step I'll do on my computer. The rest are screenshots. So when we fix this, we got the first gauge prepared statements into 100%, but then we have the token aware, and that is only at 74%. So out of my requests being sent, 26% are not hitting the correct coordinator. And if we want to look at this, the client is sending a prepared statement, but is not sending it to the right node. It's sending it to a coordinator that is not a replica. That node that received the request doesn't have the data. It needs to relay that request to other nodes in the cluster. And that's, of course, an additional hop, an additional unneeded processing. So in step 3 of the sample application, we are fixing this. And the way to do it in GoSQL is to define a host selection policy. And we have here the token-aware host policy that is defined. And once we set this up and run step 3, everything is green. Great. So we're very happy. It was very simple. We fixed 2 small issues. But now we're going to enhance the application, like it always happens. So in this example, what we're going to have the enhancement do is select the 51st, the 51st tweets he's interested in or he liked. And this is a query we try to do. So we're selecting for a specific user the ones he liked. And what are our solutions? So the first solution is to do client-side processing or filtering. So on the right-hand side, we have the query processor and memtable cache and SS table. That is a single Scylla node. For the sake of simplicity, I have a single Scylla node on the right-hand side. And we're reading from memtable cache or SS table 50,000 rows. If the probability of a user liking a tweet is 0.1%, to get to the first 50 like tweets, we need to read around 50,000 rows. But we are not processing any of that. We're shipping 50,000 rows to the client and only interested in 50 of them. It's a lot of waste. So the first solution is not great. We return a lot of data, and we're reading a lot of data off the disk. And we are interested only in 0.1% of that. Is there another solution? And the answer is yes. We can use allow filtering. Allow filtering is server-side filtering, so we can have Scylla do the filtering before sending it back to the client. The rule of thumb that you need to remember is that allow filtering should be used with large parts of the data are returned. Is 0.1% large? Well, it's debatable. It's not, it's maybe too small. So in step 4 of the application, what we did is we added allow filtering and limited it to 50 queries and ran the query. And when we run the query, we have 2 gouges alarming us. The left one at 90% is showing us that 1 out of 10 queries is using allow filtering. So 10% of our queries are using allow filtering. The graph below that shows us the number of queries. So we have here around 7 to 8 queries a second running allow filtering. On the right-hand side, we have our goodness metrics. And we're seeing there that on the gouge shows us 0%. So we're reading a lot of rows and returning only a fraction of it, close to 0% back to the client. Okay? If you look down, the graph below provides us the numbers. So we have here the rows red, 580 in my sample, or in this run. Out of that, we matched a single one, and we dropped 579 of those. Okay? So when I'm using the metrics, I can see how well my application is interacting with Scylla, and how well I'm expecting it to work. And going back to the graph, we have the query processor pulling 50,000 rows, filtering out of those, and sending back only 50. Okay? So solution 2 is server-side filtering. It's reading a lot, but at least it's returning only what the client is interested in, which is 50. Are there other solutions? So Scylla 3.0 adds secondary indexes. And secondary indexes are a way to add an index on a column and then find rows that are related to that. But the rule of thumb is that secondary indexes should be used with high cardinality. And in our case, that's not true. The liked column has 2 values, liked or didn't like. So it's very, very bad. It's worse than any other option. So we're not even going to try it out. Is there another option? And the answer is yes. Scylla 3.0 adds materialized views. And a materialized view can be thought of as an additional table that is replicating data from an existing table and keeping them in sync. That additional table can have, which we refer to it as a view, can have all the data or parts of it. But the important part is that it can have a different primary key. And for our sample that we're doing for our enhancement, it means that we want to add the liked attribute to our primary key. And if we deploy that, we get an optimal performance. Okay, we're reading 50 rows from memtable cache or SS table. Okay, again, using the materialized view, and returning the 50 back. Okay, so there's no overhead for processing this query. So we had 4 different solutions. Okay, and the question is, it's clear that solution 2 or solution 4 are the better ones. But which one should I pick? And the answer, it depends. It really depends on how many queries are going to be run. If 50% of your traffic is going to be this, then materialized view is probably the correct thing. If it's very low percentage, then it may be OK to do server-side filtering. So there's no way to know that in advance. The overhead that I'm paying in materialized view has to do with additional storage. Okay, so when I'm writing the data, I'm replicating it. So that's additional cost. So till now, we dealt with a single DC. And step 5, when we ran step 5, with solution 4, everything was great. So now we test what will happen when we move to multi-DC. And the answer is that not everything works when you switch over. So I have DC1, which is in the US. I have DC2, which is in Europe. And I want to serve my customers in the US off the data from the US, and I want to serve the customers in Europe of the cluster in Europe. But when I run step 5, the solution from step 5 on multi-DC setup, this is what I see. I see that the client is sending requests to both DCs, inserts and reads. And that means that the client is not DC aware. The client is aware of all the cluster. And once you connect the client to a cluster of Scylla, then it will connect to all the nodes. But the client is not using its location information to know with which nodes it should interact with. And that costs performance. Okay? I'm sending a request from the US to Europe. That will have an additional latency. In addition to that, there are additional metrics, and this should actually be a gauge. So when we're doing reads, we expect all the reads to be served from the local DC. We're not expecting the reads to be served from 2 different DCs. And what we can see here is that to serve a request, we have the coordinator that is sitting in DC1 sending sub-requests to replicas in DC2. And that has to do with my consistency level. So schematically, I have my client sending a request to DC1, but that coordinator node that is a replica is not able to serve that request of nodes in that DC, and it has to send the request. And in our example, I'm doing a quorum read of 6 nodes, and that means 4 nodes. So one of them has to be in DC2. So step 6 fixes both of these. So we change the quorum reads into local quorum, and we change the round-robin default policy, which is very easy to use, to DC-aware round-robin policy, in which the client provides its location information. And once we run it, all the inserts are sent from the single client running in DC1 are sent to nodes in DC1. And since we changed from quorum to local quorum, once a coordinator in DC1 receives the request, it can process the request only of replicas in DC1. In addition to the gauges that I have talked about, there are 2 other gauges that exist but are not used or not displayed in this sample. The first one is unpaid SQL reads. And the gauge itself should be 100%. So 100% of your requests should be paged. And this is a bit different. Till now, I've shown examples of things you need to change in your client application when you write it. This is something you can mess up. So the default is, for drivers, Java, GoSQL, and Python, and others, is to use paging. But at times, users think that they can do better than the server. And they will try to do paging on their application side. Okay? And you shouldn't do it. You can play with the page size, but you should not switch off paging. Botan session about work we've done over the last year will be more clearer as to why it's much, much better to leave paging on. In addition to that, there are reverse SQL reads. And the gauge is a warning gauge. Okay? Reverse SQL queries have to do with a query in which you have an order by statement in which the order is different from the base table. So let's say the base table is descending order, and the query is using ascending order. And the reason that this gauge exists is that it's harder for Scylla to process those requests. It's not as optimized. And when you see it, there is a good question. We have one customer that just started with a table with a specific ordering and ending up doing all the queries in the opposite direction. And if he used this during development, he would have detected it. Okay? Changing it now is much harder. We need to reinsert all the data. You cannot change the ordering of data inside the database already. Okay, aside of monitoring. So till now, I dealt with a lot of monitoring aspects, but we do provide you a lot of tools as well. So Avi is going to cover tools that we allow for SQL tracing. There is probabilistic tracing, slow query tracing, and client-side tracing that allows you to check what is happening with your specific queries for different reasons. We have added over the last year large partition logging. Before that, there was only a warning, which basically means that you can find out if you have large partitions and which ones exist. And we're working even to add even more. So 3.1 is going to include no-tool top partitions, which basically means if you have a lot of queries going to the same single partition, which partition is it?
Technical.
Thanks.